Hello, this is Kavyan Shandelia, roll number 24110163.
Hello, I am Kavya Patel, roll number 24110162.
And this is our assignment for the course ES-116.
Response of piezoelectric signal generator from which the signal is generated to the piezoelectric materials. We can see the signal here from the channel 1 by the yellow wave, and the piezoelectric material vibrates to the signal, which is vibration is seen by the channel 2, which is seen on the blue wave. So here we have set also the VP to 5 volts and the frequency to 1 kilohertz. So we can also see the VPP graph of and frequency and VPV C1. So here we can here from the signal generator we are changing the frequency of the input wave. So here we can see that the output wave is changing as follows. So if it increase the frequency of the wave, we can also see the VPV also are changing. So task 1 is to find out magnitude and phase response of a piezoelectric sensor, which converts mechanical vibration into electrical signal. The graph we are looking at includes two key points: the magnitude response on the top and the phase response on the bottom, both plotted against frequency. Magnitude response. The magnitude response shows how the sensor's output amplitude changes with the frequency. What stand out is the peak plot is the peak, which corresponding to the resonance frequency, the frequency at which sensor operates the most efficiently. The x-axis represents frequency and the y-axis represents magnitude, usually in decibels. At resonance, the sensor is most responsive to mechanical vibration, and we can see clear peaks in the magnitude response. This is the point where the system resonates and the energy transfer is maximized. Identifying resonance frequency. Look closely at the graph. We can identify the resonance frequency. Here we see a clear peak around the 300 Hz and 1800 Hz. This frequency is significant because it's where the piezoelectric sensor is most effective in the detecting vibrations. The resonance frequency is where the sensor experiences minimum impedance and maximum efficiency. Phase response. Now moving to the phase response below. The phase response tells us how the output signal is shifted relative to the input signal at different frequencies. At resonance, we typically observe a sharp phase change. This is due to the sensor reacting to its natural vibration. X-axis representing frequency and y-axis representing phase difference in degrees. Quality factor. Quality factor is the measure of sharpness of the resonance. The higher the quality factor means a sharper and more defined peak resonance, indicating that the sensor is more selective and efficient at this frequency. To calculate the quality factor, we use the formula Q equals to we use the following formula, where Fr is the resonance frequency and the F2 minus F1 is the bandwidth around the resonant frequency, which is the range where the magnitude phase falls to 1 by root 2 of the peak value or minus 3 decibels of the peak value. From the graph, we can estimate the bandwidth in hertz, and using the formula, we can find quality factor. Approximately quality factor for the 300 frequency is 3.53 and for the 1800 frequency is 3.6.
This is our photodiode setup. We have power supply coming from there, and the input is in the channel 1. We have an LED, a 330 ohm resistor, and in channel 2 we are obtaining output, a photodiode and a 10k ohm resistor. The photodiode is connected in the reverse bias so that minimum current passes through it. And if we block light coming to photodiode, as you can see, the voltage decreases drastically, because the more light passes, the more voltage is obtained. So our next task is to analyze the frequency response of a photodiode. A photodiode operates by converting incident light into a proportional current. We set up an LED to shine light onto the photodiode.
and modulated it using a sinusoidal input. The circuit included a load resistor to convert photocurrent into voltage, which we measured using an oscilloscope. We varied the input frequency while keeping the modulation amplitude constant, then recorded the output voltage and phase shift. The data was used to plot the magnitude and phase response. The 3 dB cutoff frequency is crucial as it tells us that the bandwidth of the sensor beyond which it is beyond which its response significantly drops. The cutoff frequency was determined by finding the point where the gain dropped to approximately 70% to its maximum value. Based on the results, the 3 dB cutoff frequency was approximately 88 kilohertz. This is important in optical communication and sensing applications since it defines the photodiode speed and efficiency in detecting signal variations. Uh, to summarize, we observed resonance in the piezoelectric sensor and calculated its quality factor, helping us understand its sensitivity and frequency response. Meanwhile, for that photodiode, we determined its 3 dB cutoff frequency, which is essential in evaluating its bandwidth. Thanks for watching. We hope this video helped in understanding the frequency response of sensors.